one of the previous videos, we have already discussed about backpropagation. I hope by now you already know what is NN and how it works, and also what is backpropagation and what way we can update the weights. All these things, I believe that you know. If you don't know any of these, please refer to the previous videos that I have on my channel. Okay, let's jump into this particular video. This is our input layer, and then followed by we can have as many number of hidden layers that we want, and finally we'll be having the output layer. From the output layer we'll be getting the predicted output. This is our output that is predicted by the model, and in order to calculate loss we need to have actual output in our data set, and we'll be having the predicted output that we get from the model. Okay, so using these two, we'll be able to tell the model that the model is performing well or it is performing bad. That information will be showing it to the model. Like once the loss is shown to the model, what the model will try to do, the model will try to update the weights, or it will try to update the parameters. And in order to update those parameters, it will be calculating these partial derivatives, or we can call them as gradients as well. Okay, so this is what it will be doing. And we know, according to backpropagation, this particular partial derivative of gradient is a multiplication of several other gradients. Okay, so this can be written as partial derivative of loss with respect to like this O of n, and here it is partial derivative of O of n with respect to O of n minus 1. Like that, so many number of partial derivatives will get multiplied in order to get this particular gradient. Okay, so and how we are writing this, basically like this output is dependent on this on directly, and this on is directly dependent on on minus 1. Like that, a backward dependency will be there, and this o2 is dependent on o1, and finally o1 is directly dependent on w1. So like that, due to this dependency structure, these many number of gradients need to be multiplied in order to calculate this particular gradient, that is partial derivative of loss with respect to the W111. Okay, this we already know, and this we have seen how it works in case of backpropagation video. If you haven't seen that, please refer to that. Now we are discussing about the main problems that are caused in case of ANN, okay, or in case of any deep learning algorithms. Okay, so the main problem it has is this particular vanishing and exploding gradients problem. Okay, vanishing and exploding gradients. Let's try to understand what is this vanishing and exploding gradients problem. Basically, as I said, this particular gradient is a multiplication of several other gradients, and what can happen is these gradients might be in the range of 0 to 1. Okay, if these are in the range of 0 to 1, what will happen, all these will get multiplied. Like let's say for example it is 0.1 and it is 0.7 and this is 0.8 and this is 0.9. Like that, if these get multiplied with each other, what will happen, this whole thing will almost become zero. So that is the main problem that will be caused, and that is vanishing gradient problem. And after calculating the partial derivative, what we'll be doing, basically according to this particular gradient descent, we'll be updating the weight, that is W111 minus alpha times loss with respect to the data, or loss with respect to the weight. And this particular gradient is happening to be almost zero. And if it is zero, what will happen, this weight will not get updated, right? So this weight is not getting updated. That means that the weight over here is not getting updated. So if it is not getting updated, that means that the model will not learn it properly, right? So this is the main problem in case of ANN or any deep learning algorithm. Okay, so if it goes to zero, then we say it as vanishing gradient problem, and that will happen when each of the gradients are having value 0 to 1. That means maybe something like 0 0.1, 0 0.7, 0.8, 0.9, like that. Okay. And similarly, there is another problem, that is exploding gradient problem. It will happen when each of these gradients are greater than 1. Like let's say, instead of these being in between 0 and 1, let's say each of these is greater than 1. This is greater than 1, this is greater than 1, like that. All of these are greater than 1. Then what will happen? All of these will get multiplied and will form a very large number. Okay. So after multiplying, it will happen to be very large number. And if it is very large number, what will happen? This will get updated too much. Okay. So like let's say this is the optimal value that we have, so we might be starting somewhere over here, and as it is too much, as the partial derivative of loss with respect to this weight is too much value, what will happen? It will jump from here to here and here to here, like that. It will not go to the optimal. We are interested in going to this point, but we will never reach this point as this particular value is very high, or in case of vanishing gradient, this particular value is very low. So this is the main problem in case of deep learning neural networks, and we'll try to avoid it as much as possible. One simplest way to avoid these things is by choosing good hyperparameters. One such good hyperparameter is choosing very good activation function. The activation functions that we have discussed are like linear, and then sigmoid, and then we have tanh, and then we have like softmax, and then we have relu, and then we have leaky relu. So these are all the activation functions that we have, and it is not good to use this softmax. This softmax is in general used for multi-class classification in the output layer. Either we'll be using sigmoid, tanh, these mostly we can use it on output layers, and also we can use them on hidden layers. But the problem with using these two functions is that it will happen that our gradient will be in the range of 0 to 1. If it is in the range of 0 to 1, what will happen? It will lead to vanishing gradient problem. And similarly, if it is linear, if it is simple linear, then almost every time the gradient might go greater than 1, and it might lead to something like exploding gradient problem. That's why it is better to use relu or leaky relu. It will make sure that sometimes the gradient is 1 and sometimes it is 0. Like that, it will try to maintain some balance in such a way that the gradients will not be either 0 or it will not be very large numbers. Okay. So this is the advantage of using this relu and leaky relu. So that's why most of the time on hidden layers, it is better to go with either relu or leaky relu activation functions. And this is not only the way in order to solve this vanishing and exploding gradient problems. Basically, we can use some other techniques like batch normalization, and also we can do something like gradient clipping. And by choosing good way of initializing weights, like that, there are so many techniques using which we can reduce the problem of vanishing and exploding gradients. But as of now, we are only like we can deal it with relu and leaky relu using such activation functions. But maybe in the future videos, not immediately, but in the future videos, we'll try to discuss all of these as well. Okay. So I hope this particular video is clear for everyone. And if you have any other doubts, please comment down in the comment section. So thank you everyone. Bye bye.